Hey audience, last time I added some new features to my signal generator and added a better DAC. I'm pretty happy with it, except for the fact that it runs so dog slow that I can only get a maximum frequency of about 200 Hz out of it. So let's do the only reasonable thing and rewrite the whole thing in hand-optimized assembly. Compilers don't produce good code, and they're no match for a human handcrafting some artisanal assembly. Handwritten assembly programs are faster and smaller than anything any compiler could write. At least, that's what I used to believe when I was younger and more naive. It is correct that you can get speed and code size benefits, but only technically correct. So let's walk through an assembly version of this signal generator and see how much we can really gain from it, and along the way we'll find a real reason to do this in assembly. I do have one, trust me, but you'll have to stick around to find out. I made the assembly version of the signal generator as close as possible to the previous Arduino one so we can make an apples-to-apples comparison. The code's up on GitHub with a link in the description, so I'll walk through it to give you an idea of the structure without too much detail. So first, there's an interrupt vector table, which I don't really need since I keep interrupts disabled, but here it is anyway. And then some notes about which registers I'm using for some variables. And then the real code begins. I make sure interrupts are disabled and then set up the stack pointer, and then I start setting up the hardware blocks that I need. This is the stuff that goes in the init function of the Arduino, and it runs when the chip gets reset. So I set up port D to use as output, then configure the ADC for reading the frequency knob, and there's actually quite a bit to do here. There are multiple modes that can automatically trigger conversions on certain conditions. I just set it to be manually triggered from software, and it has its own clock that needs to be set to an appropriate frequency, which I set as high as it can take. All of the analog input pins, along with a couple sort of reference sources and a temperature sensor, are actually multiplexed down to a single ADC, so I have to set the input source to the right pin. And there are multiple reference sources for the ADC, which it compares the input voltage to. At first I tried setting it to use this AVCC with external capacitor mode, but out of curiosity when I probed the AREF pin, I found 5 volts on it. My setup has the potentiometer between ground and the 3.3 volt supply, which would be a problem with this mode. If the reference is 5 volts but the input never goes above 3.3 volts, then I would never be able to actually set the SIGGEN to the top of its frequency range. I could fix this by either putting the potentiometer between 5 volts and ground, or by using an external AREF and connecting that pin to 3.3 volts. I ended up doing the latter. Then I set up one of the pins from port C to use for the waveform select button. Something to note here, I do set it up to trigger a pin change interrupt, more on that later. Then I set up one of the timers to count up and then reset after 1 millisecond, which I use for switch debouncing. Again, more on that later. Then I copy a set of waveform samples from ROM into RAM. RAM can be accessed faster than ROM by 1 clock cycle, and I want all of those clock cycles. Then the current sample cursor gets reset to 0, and we're ready to go. Now we find ourselves in the main loop, where I first read a sample from the waveform lookup table, write it out, and then advance the sample pointer. That all takes 5 clock cycles. Here's the corresponding code that the compiler spit out from the Arduino version. It looks like it takes about 28 clock cycles if I'm counting right. So that's a point for me there. Then I trigger the ADC to start making a conversion so I can read the frequency knob setting. Then we have to wait for it to complete, and then read the value from the ADC's registers. So the input value that we read is going to be in a range of 0 to 1023, and we need to map those numbers to a range from 25 to 2560, which are our minimum and maximum step sizes through the lookup table. The code that does this looks a bit more complicated than the one-line map helper function that came with the Arduino, but then when we compare it to the code that the compiler actually spat out, we can start to see why we might prefer the handwritten code. So the compiler's multiplication code actually looks pretty good. Pretty similar to what I ended up with, except I found the partial products and then added the partial products separately, and the compiler's code adds them along the way, which saves some temporary registers and some move instructions. So that code is likely a bit faster than mine by a few cycles. But I also think that it's technically not the compiler's code. The compiler needs a way of doing things that are part of the C language but not actually implemented by the target processor, like 16-bit multiplication in this case. So it looks like the compiler comes with a small library of functions, likely written by hand by the compiler authors, and the compiler just injects whichever functions that it needs and calls those. The compiler also does actual division here, but because we're dividing by a power of 2 in this case, 1024, we can do that much more quickly by shifting by 10 bits instead. And we can do that 10-bit shift even quicker by just discarding the lowest byte of the result, which has the effect of shifting by 8, so we only need to shift the remaining 3 bytes by 2 bits. So my code still ends up being a massive improvement. So overall, that's still another point for me. Handling the waveform selection switch happens a bit differently here. I have the push button pin configured to trigger pin change interrupts. The code never actually gets interrupted because interrupts are disabled, but it still sets a flag that we can check to see if there were any low to high or high to low transitions on that pin since the last time that we checked. So when I detect a button press, I immediately copy a new waveform from ROM into the RAM buffer and then reset the current sample pointer. It'll take some time to copy, so might as well be doing that while the switch is settling down anyway. Then I start the timer that expires after 1 millisecond, and then I wait in a loop, checking for both the timer to expire and for more transitions on the push button pin. If another transition happens before the millisecond timer is up, it's probably due to switch bounce, so we want to ignore it. When that happens, I reset the timer and then enter the loop again. The only way to exit the loop is for the timer to expire, and the only way the timer can expire is for transitions to stop happening on that pin. The timing of this isn't important since we're not outputting samples when this is happening, but I did have some trouble with switch bounce in the Arduino version, and this version works way better, so another point for me. So it looks like I'm winning by a very wide margin here. So let's take a look at these results. So let's take a look first at the compiled version with the knob turned to the highest frequency setting. About a 4 millisecond period, so about 250 Hz. Then the artisanal assembly version, about a 3 millisecond period for about 333 Hz. The period is about 3/4 that of the compiled version, and the frequency is about 25% higher. That's not terribly impressive, but hey, it's not nothing either. That's a non-trivial improvement. Have you ever had that feeling that you've missed something really important? Something that should be obvious, but you just can't quite put your finger. Just for curiosity's sake, let's reload the compiled Arduino version back onto it and see what it's using for its ADC reference voltage. Well, 5 volts, so I was never actually setting the compiled version to its highest frequency setting. Rather than fix it, let's just force it to the highest frequency setting and see what happens. Well, so let's take a capture of this and then force the assembly version to the highest frequency setting the same way, just to be sure that they're running the same number of steps through the lookup table per loop. So all that work, all those code improvements over the compiled version, and it literally makes no observable difference in the end. So the problem here is that while my assembly code runs much faster than the compiled code, it turns out that the program actually spends very little time actually running code, and way more time sitting around waiting for the ADC conversion to finish. The ADC is a successive approximation converter, which means it's basically playing that number guessing game where after each guess you get told if your guess was too high or too low. For each of 10 bits, it converts its guess into an analog signal through a DAC and then compares it to the sampled voltage. These signals need to run through analog circuitry, which is a bit slow, so it needs a slow clock. And according to the datasheet, it takes 13.5 ADC clock cycles. And since each of those ADC clock cycles is 128 system clock cycles, that's a total of over 1,700 system clock cycles. We could probably run 1,200 to 1,500 instructions in that time. We could output over 200 samples from our lookup table if we were doing nothing else. And that's all in the space of time between one sample and the next in this code. Do we really need to wait for this thing to finish before writing out more samples? When the knob gets turned, we don't really need the frequency to update immediately before the next sample. Just quickly enough so that the human turning the knob won't notice a delay. So let's just output more samples within this busy loop while we wait on the ADC. So with 5 microseconds per division, that's a 15 microsecond period about, so that's like 66 kilohertz there. We actually got about a 200x improvement. But now it looks like absolute dog. So why is that? Within the busy loop, we output a couple hundred samples back to back to back with only a few instructions between them. Then when the ADC finally finishes, we run through all of this other code before the next sample, and now this delay is significant. So when we get back around to the busy loop to output fast samples again, we've been delayed by a noticeable amount, and the waveform starts back up but offset in time. And that's why we see these ghost images on the scope. Those are traces where samples got delayed and then started back up later than expected. But knowing what's been holding us back gives us a path forward, and 66 kHz is well above the range of human hearing, so this signal generator should be easily suitable for any audio projects if we can clean up that output. And that is something that we'll only be able to do with good old-fashioned, specialty, handcrafted, artisanal, locally grown organic, no antibiotics ever assembly code. But that's for the next video. I'll see you then.